Now, NTP synchronization between, so when the client goes to the server saying, give me your time, what is your clock, let me also synchronize that, your clock with mine, let me synchronize my clock with yours actually. Synchronization may take time because time update is being done incrementally. So it's going to take longer based on the time difference between client and server. So what this means is that if router 1 is going to be the NTP client, and router 2 is the NTP server. And before the client speaks to the server, the current time of router 1 is 9 of May 2015. On the server, which is accurate, is whatever, 10 of June 2016. So when the client goes to the server saying, hey, what is your time? And of course the server is going to reply back. Then the client is going to get up to date with the server's time, not like in a snap, like in one message. They're going to constantly go back and forth. The client is going to tell, so when the client says what's your time and the server says this is my time, pretty much, client is going to adjust a bit his local time to be closer to the server, and then the client is going to constantly go to the server again, what is your time, here's my time, and so on. So the longer the time difference between the client and the server, and of course based also on the platform, the longer it's going to take for the client to get synchronized with the server. Now NTP also supports authentication, which is highly recommended for security reasons. It is meant to prevent NTP clients to synchronize time with spoofed NTP servers. For example, given the previous setup with the client and the server, let's say that router 1 so they run NTP unauthenticated, and router 1 goes to the server on an IP address of the server being whatever 5552. It's a UDP packet saying give me your time, and the server replies. But because this is a connectionless session, it runs on top of UDP, it means that clearly somebody, an attacker, like for example PCB, could send an NTP packet to router 1, NTP packet sourced from 5552. So spoofing. So PCB knows that that client has a server 5552, and it's going to send a message to router 1 saying, hey, this is your new time, which is going to send, of course, router 1 a wrong time and date in there. So we want to prevent against this kind of very basic NTP attack by doing authentication. So ideally you should also always put NTP authentication in place. Now NTP supports only MD5 authentication. You might state, well, what is that? Why is that? Because MD5 has a lot of, let's say, collision attacks, a lot of flows in there. It's not as secure as SHA is. Correct. But pretty much on highly secure networks, in those networks, those companies are not running NTP, but are running PTP, Precision Time Protocol, which is a better version of NTP. And it provides like nanosecond or even picosecond level, let's say, synchronization time-wise between the client and the server. And PTP supports actually SHA-1 and SHA-2 as the authentication method. So if you want high security, you're going to run PTP. If you want, regular security, MD5 is going to be good enough. So because authentication, and this is a big confusion with how NTP authentication works, because we configure NTP authentication with the scope to prevent NTP clients to synchronize time with spoofed NTP servers. It means that when you enable authentication of NTP, what's going to happen is that NTP client authenticates the time source, the NTP server, but the server does not authenticate the NTP client. So it's very important to understand that. Because again, if you understand I mean, there should be no confusion if you understand what is the scope of authentication. We want to prevent the client not to get synchronized with a spoofed NTP server, which means the client has to authenticate a server, and that's it. So it makes sense that a server does not authenticate the client. So pretty much how this works, of course, authentication is going to be configured on both the server and the client for MD5 to work, but the server does not authenticate the client. What's going to happen is that the client, so router 1 is the client and router 2 is the server. Router 1 is the client and router 2 is the server. What's going to happen, router 1 is going to send over to router 2 in the NTP packet a key number in there to be used for authentication. And router 2 is going to look in its configuration, okay, do I have that key? What is the key string in there? So in router 2 is going to send back to router 1 the NTP packet. That NTP packet is going to, of course, use the key number, likewise, the same key number, and the MD5 hash to that packet. So now when router 1 receives that packet, of course, it's going to recompute the MD5 hash, compare the MD5 hash with the MD5 hash attached to the packet, and if they match, it means that the packet came in from the appropriate server, because only that server should know the key number and the key string in there. Configuration-wise on the iOS, for the NTP server functionality, we have to enable the NTP server role if you want the iOS to be a server, and if the clients are going to be authenticating the server, then we have to also enable support for client authentication, which means on the server we have to configure the authentication key and the key string, and also configure the key as trusted. This is by design of FTP, but not of FTP, of NTP. So not only you have to define the key and the key string, but also you have to define the key as trusted. Now, pretty much depending on the iOS code or whatever code you're running on other devices, it may not be needed to put the key as trusted. So pretty much back in the older codes of iOS, the trusted key was not needed to be configured. But now CISCO, of course, has changed that around for a long time ago from 12.4 something, the iOS code. So ideally, just to be on the safe side, you always have to also configure the key to be trusted. So trusted means that both the server and the client, in this case the server, trusts that key to be used for authentication. Because the server may have multiple keys configured, but not all of them may be used for authentication actively. Only the trusted one can be used for authentication. Now on the client part, the client configuration is going to be the same steps on both the iOS and the SA. If we want authentication, we're going to have to optionally configure or authenticate the NTP, which means the first step is that on the client we have to enable authentication. This step was not performed on the server because, again, the server does not authenticate the client, only the client authenticates the server. So you have to enable authentication to begin with of NTP packets, then likewise to configure the authentication key and key string to match as configured on the server, and likewise configure the key as trusted. So you see it's one more step on the client side because only to enable NTP authentication, because only the client authenticates the server, not the other way around, and it makes sense. And in the end, you configure the NTP server, of course. So we tell the client what is your NTP server, and when we define the server, we have to also specify the key number, because based on that key number, the client knows what is the key string. So based on the key string is also based on the key number configured at the NTP server configuration. So when you go on the client and say NTP server, whatever the server is, and you bind the key, then the client is going to know, okay, is that key trusted? If it's trusted, I can use it. And based on the key number, is going to know what is the key string. So going to be able to properly perform and authenticate the NTP packets received from the server. Verification wise, on both iOS and SA is the same verification commands. You verify if time is synchronized, show NTP status. It should show up as synchronized. And lastly, you verify if time source is also authenticated, show NTP association with or without detail. Okay, before we go to the configuration part, there's a question from Matthew. Christian, can you explain single sign-on? So to give you an example, single sign-on, for example, let's assume that PCA, it is going to initiate, let's say, this is the example that came to my mind now, so it could be a lot of other use cases. PCA went to, before we get going, you should always again think about the naming, what the name says is going to do. So SSO stands for single sign-on, which means I would want something that once a user has configured a password, has authenticated in one place, I don't want the user to get authenticated in other places as well. So what this means is that once the user gets authenticated in the network, then if the user tries to access resource A or B or C, he should get authenticated transparently without being asked for the credentials again. This is what they call it, single sign-on. Like a more complex example would be that PCA has an SSL VPN session to ASA3, SSL VPN session, which means it's going to get authenticated via username and password. Let's suppose that. So PCA is going to put in the to get authenticated, username of ABC with password of XYZ. So it was authenticated via username of ABC, password of XYZ. Then the VPN tunnel is up. Is going to be a client as SSL VPN tunnel. And then in the portal, in the SSL VPN portal, DSA is going to publish an HTTP URL as a bookmark to server A. So what a user does through that SSL VPN tunnel is going to click in the portal of DSA to get access to that server A. So as the user tries to access that server through the SSL VPN tunnel, in general that server is going to ask again for authentication. In this case, what SSO is going to do is that once the packet goes to server A, the ASA is going to transparently inject the username of ABC and a password of XYZ to be sent to that request to the server. So the server does ask for authentication, server A, but the ESA is going to pre-populate the credential used by the user to authenticate when the SSL VPN tunnel came up, so that this means it's transparent from the user's point of view. So even though technically speaking, the user should be authenticated by server A, that happened behind the scenes transparently, user was not aware of that. So this is single sign-on. The user has signed on a single time, and then when he accesses whatever resources, which also those resources require authentication happens transparently behind the scenes. Like another use case would be, for example, if let's say this is our network in here. One easier example, this is our network, and this is our web security appliance, CISCO's proxy, which means, so this is the web security appliance, CISCO's proxy, which means all traffic, all web traffic leaving the network is going to be inspected by that engine to be allowed or disallowed based on the policies and if the traffic is malicious or not. So another use case of single sign-on is that if the web security appliance is integrated with Active Directory, with AD services, when this user on this PC logs in, he's going to also get authenticated to Active Directory. As he logs in on the PC, gets authenticated via AD services. And so that's being done as the user logs in on his computer. And then when a user has to send any web traffic in the network, which means the traffic the user sends in network web traffic, that web traffic goes to the web security appliance. And the web security appliance is going to ask for authentication. Then by default, the user's browser is going to transparently, not prompt the user to authenticate, but send the credentials, username and password, over to the WSA without the user being prompted. So the user gets authenticated by the WSA without even knowing, because that happens behind the scenes. So again, it's another way of single sign-on, because the user just logged in on its computer, then he opened the browser, then as he typed in www.google.com, the WSA has said, well, I have to authenticate you, and then the browser by itself transparently has picked up the Windows credentials, sent those to WSA, and WSA has validated those against AD, and authentication was successful without the user even knowing to begin with.